Hello everyone and welcome! It's great to see you all here today. We're going to dive into a topic that's crucial for many of us working with cloud databases. Amazon RDS for Postgres, specifically looking at its transaction isolation guarantees under the microscope. This is based on some recent independent research, and the findings might surprise you. Let's get started. So what's on the agenda today? First, we'll briefly touch on Amazon RDS Postgres, particularly its multi-AZ feature, which promises high availability. Our main focus, however, will be on the transaction isolation guarantees. Specifically, does it deliver what we expect? We'll then walk through the findings from an independent Jepsen investigation into this very question. And finally, perhaps most importantly for everyone here, we'll discuss the practical implications of these findings for you as users. Sound good? All right, before we get into the weeds, let's quickly establish some common ground. As many of you know, PostgreSQL itself offers several transaction isolation levels. You've got read committed, the default, then there's repeatable read, which in PostgreSQL actually implements the stronger snapshot isolation, or SI, and finally, serializable. Now, when we talk about RDS multi-AZ, the key feature is synchronous replication for high availability. You interact with it typically through a primary endpoint for reads and writes, and often a separate reader endpoint for scaling reads. The strongest isolation level we generally expect to work reliably across both these endpoints is snapshot isolation. Keep that SI expectation in mind. This brings us to the central question we wanted to answer. We expect snapshot isolation, especially when using both primary and reader endpoints in a multi-AZ setup. But does RDS actually deliver on this promise in the real world under concurrent load? Is the isolation as strong as we think? This is precisely what we at Jepsen set out to verify through rigorous testing. So how did we go about testing this? We employed the Jepsen framework, adapting our existing Postgres suite specifically for the RDS environment. We provisioned standard multi-AZ clusters, nothing unusual, just typical dbm6id.large instances. Our workload involved concurrent transactions reading and appending unique integers to lists stored in database rows, hitting both the primary and the read-only endpoints simultaneously. This kind of workload is great for uncovering subtle consistency issues. And a critical point here, we deliberately didn't inject any faults. No network partitions, no node crashes. We were testing perfectly healthy clusters under normal operation. And the results? Well, they were definitely surprising. Even on these healthy, unfaulted clusters, running a moderate workload, we consistently observed violations of snapshot isolation. Let that sink in for a moment. These weren't rare, once-in-a-blue-moon events. These anomalies popped up every few minutes during our test runs. And as you can see here, this wasn't tied to a specific version. We saw this behavior across the entire range AWS supported at the time, from 13.15 right up to 17.4. Let's make this more concrete by looking at a specific type of anomaly we observed, known as long fork. Imagine 4 transactions, T1 through T4. T1 writes to list A. Later, T2 reads list A and successfully sees T1's write. Okay, seems normal. Concurrently, T3 writes to * different stems list B. And later, T4 reads list B and sees T3's write. Still seems fine, right? But here's the kicker. T2, despite seeing T1's write, sailed to and homes to see T3's write, and T4, despite seeing T3's write, sailed to see T1's write. It's like they existed in slightly different realities. This specific pattern, this long fork, is a direct violation of snapshot isolation. Why exactly does long fork break snapshot isolation? Remember, the core promise of SI is that each transaction operates on a single, consistent snapshot of the database, as if it were taken at one specific moment in time. This implies a linear ordering of events, but long fork creates a paradox. T2 seeing T1, but not T3, implies T1 must have committed times before times T3. However, T4 seeing T3, but not T1 implies T3 must have committed 1 3 before times T1. You can't have both T1 before T3 and T3 before T1. It's a logical impossibility within the SI model, contradicting the linear history we expect. Okay, so if it's not standard snapshot isolation, what could it be? Based on our observations, specifically seeing long fork anomalies but not seeing other types like right skew in our tests, our leading hypothesis is that RDS multi-AZ might actually be providing asterisk parallel snapshot isolation asterisk, or PSI. PSI is a known, formally defined consistency model that is subtly weaker than standard SI. Crucially, PSI allows anomalies like long fork, where transactions can disagree on the ordering of other concurrent transactions, while still preventing things like right skew. This pattern fits our findings quite well. So let's bring this back to practical terms. What does this potentially mean for you as users of RDS Postgres multi-AZ? The main takeaway is that the isolation guarantee might be weaker than you assumed, particularly if you're comparing it to single-node PostgreSQL. There's a tangible risk that read-only transactions hitting your replicas might observe state that appears inconsistent or out of order relative to the primary, manifesting as these long fork anomalies. Have you built systems relying heavily on replica reads for consistent views? You might need to reconsider. Think about your critical read paths. Perhaps they should always go to the primary? Or maybe ensure that transactions needing strong consistency always perform a write, which could potentially force better synchronization. These are important considerations. All right, let's quickly summarize the key points. Our independent Jepsen tests indicate that Amazon RDS Postgres multi-AZ across multiple versions does not consistently provide snapshot isolation when using both primary and reader endpoints. The observed behavior, specifically the presence of long fork anomalies, strongly suggests it might be operating at the level of parallel snapshot isolation, which is a weaker guarantee. Therefore, we strongly advise you to review your application's consistency requirements, especially if you rely heavily on read replicas. Understand if your transaction patterns are vulnerable to anomalies like long fork. This research was conducted independently by Jepsen, and you can find more details on our website. Thank you.